My topic of presentation is technique and best practices of low power design methodology for 2D mesh NOC. Myself, Dr. Sudhir Shelke, Principal, Guru Nanak Institute of Technology and Director, Guru Nanak Institution, Nagpur at VIT Expo, World Innovation and Technological Expo Investment Summit 2020-23. Thank you all for giving me an opportunity to present my research work over here on this particular conference. Abstract of my research is I have optimized architecture, that was generic architecture of 2D mesh NOC that have been optimized with advanced technology that resulted into low power consumption. It is further optimized by using the low power compiler from Synopsys using SEED 19 nanometer technology that I have worked on the 19 nanometer technology. In this design of 2D mesh NOC, power and area optimization with gate level power optimization, power is obtained and that power is reduced by 77% and area is reduced by 45% of generic architecture of 2D mesh NOC. Therefore, I can say the low power design methodology used in this design resulted into improvement of the chip design significantly. The necessity of low power design is the low power design comes from the following reason why these low power designs are highly required for the reduction of this dynamic and leakage power. So for the chip used in products supplied by the battery such as portable computer and handheld devices. Secondly, with the steadily increasing of the chip capacity and density, as you know that Murray law says that as you go on increase the number of transistor on a chip or on a die, ultimately more power is required and that particular power will convert it into dissipation of the power and that particular power has to be reduced by using some technology or techniques. That techniques are low power design techniques. So low power design is also required to reduce the power in high-end system with huge integration density and thus improve the speed of operations. Ultimately, it will result into speed of operation. To minimize the power dissipation, specifically with low power methodology in design system, the method should be applied all over the design from system to process level. It is highly required to apply it all over the design from system to process level. The aim of low power design is to minimize the individual component of the power as much as possible, hence decreasing the total power consumption, that is switching and short circuit power make up the dynamic power, whereas leakage current that passes through a transistor make up the static power. So ultimately these two powers, that is dynamic power and leakage current, has to minimize significantly and the techniques provide to reduce this particular power, that is short circuit power, that is nothing but the dynamic power, and leakage current that passes through the overall transistor and that make up the static power, and these two power has to be reduced significantly and that would be resulted into low power design methodology techniques. So this is low power design flow implementation, the flow which I have implemented for reducing this particular dynamic and leakage power. So ultimately high level design is nothing but the code which we written into this particular editor and that particular high level design would be converted into a RTL. By RTL, this particular flow shows that RTL power analysis, pre-layout gate level power analysis before optimization, pre-layout gate level power analysis after optimization, and post level gate level power optimization. So these two would be at the floor planning, this would be at the beginning level, and ultimately to estimate the particular accurate and actual power we need to have the layout designing. So this particular will give the estimated power, what would be the power or it estimated the battery requirement of the particular devices, and ultimately actual power will be decided at this particular post layout designing. So these are the SDC, that is Synopsys design compiler, and this is power compiler, and ultimately using this design compiler and the power compiler, ultimately you can target it the estimated power of the design and ultimately it would be converted into the actual power which is required for the particular portable device. So the design flow comprised of three types of three types of power analysis and two kinds of power optimization technology. These are the three kinds of power optimization analysis. That is, one is RTL power analysis. Second one is pre-layout gate level power analysis. That is before optimization and after power optimization. Secondly, post-layout gate level power analysis. Then RTL simulation for pre-layout gate level simulation and post-layout gate level simulation. Power optimization methodology which I have used is clock gating, focus on optimization of timing and power, and gate level power optimization which are implemented further of clock gating is focuses always on optimization of the power as well as timing and area. So what actually happened in this particular power analysis flow? So by using the clock gating, this clock gating is power saving features in the semiconductor. As you know that we are using this handhold devices like mobile and all, it requires that this power of the design has to be reduced. Okay, as you know that whenever you're using this particular mobile, number of blocks will be ultimately used in that particular one, and that blocks are required to be controlled by using this particular clock gating techniques. That means the block which is required to be controlled, that would be a switch off, and the block which is required to be on, that would be on. So that would be done by the clock gating. The blocks which required to give the clock would be given, and the block which is not required to be given, that would be switch off. So ultimately clock gating means, clock gating is the power saving features in semiconductor chip that enables the switching of the circuit. Many electronic devices uses clock gating to turn off the buses, likely controller, bridges, and part of the processor to reduce dynamic power. So the clock gating is ultimately useful to reduce the dynamic power. So what is this RTL? RTL create SGL to high level representation of the circuit. Whatever code we used to read, right, that would be converted into high level representation of the circuit. That means code would be converted into the circuitry. That is by using the RTL. So that RTL this RTL is given to RTL simulation, then it is also given to the set file, and again ultimate power analysis is done repeatedly, so that it would be giving the estimated power of the circuitry. So what is this RTL simulation? So RTL simulation to verify the logic without delay. So that used to be verify the vectors, whether that particular vectors is logically correct or not, and it would be like logic without delay. So, and output of this RTL simulation is given to shape file. It is shape file. Shape file is nothing but the switching activity interface format. It contains information about static probabilities and toggle rate of the circuitry. It used to check what is the static probability of that particular circuitry as well as the toggle rate of the circuitry. Then if you see that this high level design is converted into circuitry, and that particular circuitry is given to the clock gating, and clock gating is the technique by which we can reduce the dynamic power. Now this clock gating output is given to the synthesis, and synthesis is the process by which we can convert this particular RTL to gate level netlist. So gate level netlist means this circuitry is converted into the gate. So one of the input to this particular synthesis process is SGS. Okay, that is synopsis compiler. That is nothing but the synopsis compiler, and that is to be done at the pre-layout gate level power analysis before optimization to get the estimated power of the device or to get the estimated power of that particular chip. Again the netlist, again the same process is being repeated. Okay, and now this is at the power compiler, and this is at the design compiler, and this is at the power constraint, that means power compiler. In this particular third block, this design compiler and power compiler used to be worked together so that it would be given the exact and actual power of the design. So SDC is nothing but the synopsis design constraint or compiler. Synthesis is the process to convert RTL to gate level netlist. Netlist is nothing but the connection between the gate, resistor, capacitor, and the transistor. and gate level power compiler and design compiler are used to estimate the targeted power, and ultimately this particular targeted power is given to this particular course layout, and course layout used to determine most actual and accurate power analysis obtained, and ultimately that estimate power would be converted into the accurate power, and ultimately we can decide what type of or what would be the power requirement or what would be the battery requirement of that particular device. So this power compiler used in the following aspect: performing power analysis at RTL and gate level, that I have already done. As guide architecture, that was the generic architecture designed for the saving of the power. Achieving the power reduction by RTL clock gating and gate level power optimization. Firstly, the power is achieved at the RTL clock gating, that is desired power, and further by using the power compiler, gate level power optimization is used, and ultimately it is giving the significant reducing of the power, that is leakage and dynamic powers. So this is continued with this. As this is the Moore law, this particular this diagram is of the Moore law, and this is all the devices nowadays we are using for day-to-day activities. So Moore law shows that as you go on increase the transistor on a chip or number of transistor on a chip, ultimately there would be huge number of leakage power and dynamic power. So that particular leakage power and dynamic power has to be reduced significantly. So what I can say, the speed of the transistor is continues to improve, and the most commonly used technique to achieve the high performance is to reduce the geometry of the transistor as well as the voltage to operate it. That means we have to see that geometry of the transistor, that means minimizing the power, at the same time minimizing the voltage requirement. Ultimately that could be done by using the particular reduction of the power and area. To maintain the speed and noise margin of the smaller transistor, the threshold voltage need to be lower too. Since the threshold voltage has exponential impact on the transistor leakage power, low threshold voltage transistor have high leakage power as shown in the figure. As you know that high transistor performance switching speed, so lowering this particular leakage. So ultimately that has been achieved. So in this research work, based on the application of the power compiler in the design, the method and effect of the power analysis are obtained, and that obtained by using clock gating power optimization and gate level power optimization. So what is comparison between these two optimization technique? Why this further gate level power optimization to be done to further reduction of the dynamic and leakage power? So what is this clock gating at the RTL, gate level and power driven? So power optimization at high level of abstraction has a significant impact on reduction of the power in the final gate level design. Means clock gating is an important high level techniques for reducing the power consumption of the design. Further reduction can be done at the designing level, that is at the system level. So gate level power optimization being used for that. During an optimization session, power compiler performs additional steps to optimize design for dynamic and leakage power. So as I told in that particular flow, why this particular design compiler comes in existence for reduction of the optimized design for the dynamic and leakage power. So during an optimization session, power compiler performs additional steps to optimize design for dynamic and leakage power using fully characterized libraries that containing variety of the cells with different drive strength characteristics. So inserting gate level power optimization in the particular design, which I already decide what kind of the particular inserting gate level power optimizations to be done. So this is another flow at RC level. The input of the gate level power optimizations are, very first is RTL or gate level netlist. So RTL or gate level netlist and power plan. So this particular is the RTL or gate level netlist, as I have said previously, that to be given to optimization logical synthesis. So another input to this particular power optimization logical synthesis is power option. So power option enable the power optimization. So start with the power optimization. Then libraries having the different varieties. Power compiler select the different library cells to rebuild the netlist with the optimized power. So every netlist has to be rebuilt for the optimization of the power, and that is available with the particular library. One of the particular library to be selected to optimize this particular leakage and dynamic power. So multi-level voltage threshold libraries are highly recommended for leakage optimization. As I said that this leakage current is highly reduced, and that would be reduced by using the high voltage threshold libraries. So what is switching activity? This is switching activities. This is required for dynamic and total power optimization and used for the high accuracy in leakage optimization. Lastly, this output of the gate level, this output of the gate level power optimization is a new gate netlist that has optimized power by using all these particular inputs. The optimization is implemented with the compiler or compile ultra commands that to be used for further at the output level. So inserting gate level power optimization in synthesis flow. This is synthesis flow, that is RTL to be converted into gate level, and while converting this particular RTL into the gate level, we have to follow this particular synthesis flow, and the synthesis flow shows the steps involved in power optimization in the synthesis flow for presented ASIC based NOC, that is ASIC application specific integrated circuit, and that for this particular network on a chip, which was the generic architecture previously, and that generic architecture we have used for the testing. So for flow for the synthesis power optimization, as I told that, so this is HDL file, and that has to be given to the library. We have to set the library accordingly. So we have number of libraries available. So link library, target library, physical library, symbol library, and synthesis library. And this particular specific library is to be given to the design, that is read design. So we have to have the read file, and this particular again to be given to design environment, having the number of design environment over here, that set operating conditions. What would be operating condition? That means thermal conditions. At what particular thermal condition this particular chip has to be operated, or chip has to be designed. Set wire load model, then set a drive, set a driving cell, set load fan outs and fan in, set minimum library, and this particular again to be given to get design constraint. As I told that there would be a number of power constraint and design constraint, so that design constraint also has to be set. So set all these are the environment. So how this transistor, set maximum fan out, set maximum capacitance, create the clocks. Create the clocks means to which particular block that clock has to be given, and to which particular block that clock has to be not given, which block has to be turned on and which block has to be turned off, which is in the use or which is not into use, that has to be decided. So set Am I audible? Optimize the design, compile ultra.
Okay.
Am I audible to you all?
Yes, please. You're audible.
Yeah, yes. So further step is optimize the design, that by using the compiler ultra command has to be set to go for particular one. Analysis and resolve the design problems, and to analyze this problem we have to set this particular libraries like check design, report area. That means whatever the design has been inputted, that is available for this checking or not at the particular level. The report area, what report area means, what is the requirement of this particular area at particular layout level. Report constraint, what would be the power constraint of that, what would be the timing constraint of that. Timing constraint is always used for the operating frequency and operation of the particular chip, and ultimately this particular area's timing as well as the power would be estimated. Actually it would be estimated for the particular chip, what would be that particular power, area and timing requirement to design the particular SOC or NOC or any sort of chip. So this is how we can do that particular further at gate gate level power optimization in synthesis flow. So ultimately, when I compare this design, previously generic design was made up by using the D flip-flop, and whatever I have used this particular, that is by using the SRAM. So D flip-flop is converted into the SRAM in my design, tested design, and ultimately for this particular SRAM design, I have used this gate level power optimization, and you can say previously the area of that particular chip was this one. By using the D flip-flop and by using the SRAM, the area is significantly reduced by using the gate level power optimization, and ultimately that area is reduced by 43% or 43.669%, and this power previously it was consumed 10.7 milliwatt, and that has been significantly reduced is at 2.45 milliwatt, and ultimately this area is reduced by 43.66%, and power is significantly reduced by 77.1028%. So I can prove that whatever the technique I have been used for the particular, that is significantly used and it is very much correct and approximate. Therefore, I can say that gate level power optimization is an important high level technique specifically used for the reduction of the leakage power consumption for a design. Therefore, power consumption is optimized with power compiler from Synopsys using SAED, that is seed 90 nanometer technology process. In the presented design, the power optimization with gate level power optimization technique is approximately 77.10 and area is optimized by 43.66%, and it is when it is operated at the clock frequency of 920 nanosecond, report of which is shown in the figure and comparison is shown in table. So this is how it is significantly reduced. So it is reduced by this 77%, and this area is reduced by this particular 43%. So this is how comparison has been done. So this is done at FPGA level as well as the ASIC level. So FPGA level by using this technological library of FPGA. So work at the core port, and ultimately power requirement is 10 milliwatt, and these are the slices which is used in FPGA. So again, I have tested in the another technology, and that is with I have tested at both 4 port as well as the 5 port. Ultimately, power requirement is this, and slices uses with this it is highly reduced. So this is at the ASIC level. So technology I have used, as I told, it is 90 nanometer ASIC process. Okay. So what was the design available was ASIC with D flip-flop, which is having the 4 port. Power requirement was 10.7 and area requirement of this. ASIC SRAM, this D flip-flop I have converted it to the SRAM. So that was with the same port, that is 4 port. Drastically 10.7 is reduced by 3.7 and area is reduced to this 15.150314. Then again, a number of clock gating techniques I have used. So ASIC with the RTL clock gating with 4 port, again significantly reduce the power as well as the area. ASIC gate level at clock gating with 4 port, it is 3.50% milliwatt. Ultimately, this area is this much. Another technique that I have used is ASIC power driven clock gating techniques with 4 port. Again, it is drastically power is reduced, area is also reduced. ASIC gate level power optimization with 4 port. So 10.7 is ultimately reduced to 2.45 milliwatt. That means power requirement from 10.7 milliwatt is reduced to this one, and ultimately we have optimized this particular power by using all these particular techniques, and ultimately this area is become half. That is, it was like 20 and it is up to this 11.4195. So ultimately I can say whatever the particular technique I have been used, that is significantly used for the reduction of the leakage and dynamic power, so that I can conclude and say about that present research work emphasize on the use of the techniques to reduce the power consumption of complex SOC or NOC. SOC is nothing but the system on a chip. NOC is nothing but the network on chip. I work on the network on chip design and the technique used which result into improvement of the chip design significantly. So these are the references which I have used for this one, and ultimately I have presented number of papers and as SCI, Scopus journals, IEEE and all. So this is about my presentation, and thanks everyone for giving me an opportunity to be one of the presentee of this STEAM conference. Thank you one and all.